multi-core processing and flight software.
Hi, I'm David Edell from Applied Physics Laboratory to talk about flight software architectures for flight systems. So, as you know, multi-core systems have become the standard for your home computers now, and they're slowly making their way into cell phones, and now they're beginning to come out for spaceflight systems. Aerofix has the GR712 and Leon 4, which is dual-core or quad-core systems. We have two of those in our lab that we've been experimenting with. As part of a joint IRAD between us and the Goddard Space Flight Center, we looked at the architecture for flight software and multi-core systems, specifically extending the Core Flight Executive, or CFE, which is a message bus standard developed by Goddard to be used in multi-core systems. We've looked at both AMP and SMP systems, and our primary focus was on SMP, but we did do a little bit of investigation into AMP. Now, what's asymmetric versus symmetric multiprocessing? Well, a traditional single-core system would be uniprocessor systems, or UP if you're looking at VxWorks documentation. Asymmetric multiprocessing is where on a multi-core system, each core operates as an independent system with a completely separate operating system, whereas in symmetric multiprocessing, the whole system works in unison so that there's one operating system controlling all the cores. In AMP, each operating system, as I said, is independent. Standard interprocessor techniques can be used for communicating between cores, such as shared message queues or a loopback network, but this depends on OS support, and it's normally an extension of the operating system using shared memory or hardware. Hardware resources are normally allocated to a specific core in AMP, same thing for SMP as well. VxWorks does support asymmetric multiprocessing, although it does not support it for the Leon 3 given the current BSP. RTEMS does support AMP, and we did briefly investigate AMP, which I'll talk about in a few minutes. The main difference in AMP versus traditional system is you basically build a separate image for each core, which needs to be loaded separately. Symmetric multiprocessing, it's a single operating system for each core. The OS dynamically assigns tasks to run on whatever core is available based on task priority and CPU affinity, meaning you can choose which tasks the process may or may not run on. The Leon BSP for VxWorks 6.7 supports SMP, and that was our primary use case for this IRAD. Linux also supports SMP, so CFE is also capable of being run on the Linux system for development, so we also extended it to run SMP on Linux for testing. Okay. So, I mentioned task affinity. Symmetric multiprocessing mode, affinity is basically a bit mask that states what cores a process can run on. It can either float, in which case it'll run on any core as CPU resources are available and using the normal priority allocations. Or you can set the affinity to run on a specific core, or if you have more than two cores, a specific set of cores. The APIs for setting affinity are very similar in both VxWorks and Linux. The details, the semantics change a little bit, but the functions are basically the same. So, how do we extend this to flight software architecture? CFE uses something called the OSAL, an OS abstraction layer that serves as a middleware between your applications and the operating systems, so you don't use the calls directly. We've extended this to add support for multiprocessing capabilities. Specifically, when a task is spawned, you can pass in a task affinity. If you're running on a system that does not support SMP, then the OSAL will just stub it out and continue operating as normal, or give an error if you're giving it an illegal value. In other words, a core that doesn't exist. All API changes that we were making for the OSAL were backwards compatible with previous implementations. For the CFE itself, when a CFE application starts, you tell it which core or what affinity you want it to execute on. Once the system is functional, other APIs are available that you can dynamically change the affinity, what core process is running on at runtime. This basically allows a mission the flexibility to choose how to allocate resources on the system. For example, you can allocate specific tasks to specific processors. For example, lock a CPU-intensive analysis task to one core, or you can have them float using whatever resources are available in the most optimum approach. Mission chooses whatever is appropriate to it and can change modes based on the current mission scenario. Now, previous IRAD for last year's IRAD and CFE, CFE was extended to support the MMU, with Memory Protection Unit. So, in that mode, under VxWorks, for each RTP MMU protected thread, it's running in a separate process, and it has a complete instance of CFE running in it. For this year, for the multi-core, we've extended it so that the same interface runs on the multi-core system. The way VxWorks works, basically no changes are needed to go from single core to multi-core systems. The image is compiled a little bit differently, but the code remains largely the same. The main difference is how tasks are spawned. So for CFE, we've modified it so when you spawn a thread, you assign an affinity to that. The default affinity for a thread is inherited by all tasks spawned within that thread, namely each of our CFE applications. In addition to that, when you spawn an application, within each CFE instance, you can choose which core, what affinity it'll run on. As I said, changes to run multi-core environments, in general, you don't need to make much changes to the code itself. The same inter-process communication techniques you use for a single core system works in the multi-core. The difference being, instead of a simulated multi-threading, obviously you have real multi-threading. But that does mean when you're using hardware locks, such as task interrupts and interrupt locks, that applies only to your current core, not to the entire system. So if you depend on that for, say, locking the system while you're doing a critical resource, you have to be aware that it'll only apply to the current core while other tasks are still running. Other techniques are available, such as spin locks in the multi-core. Spin locks in VxWorks is backwards compatible, equivalent to a semaphore on traditional VxWorks. Main difference for a spin lock is it'll keep busy waiting, so you're waiting for a task in another CPU to finish without giving up CPU resources. So, moving on to our experiences using VxWorks. Board support package for Leon 3 is, well, first of all, support for SMP was added for VxWorks 6.7. The VxWorks BSP supports it, but this is an early release. And this is also the first time we've used the MMU gate-based capabilities on the Leon 3. As a result, there is some learning curves, and we have encountered a number of issues this year in using the BSP. As we've gone through it, Geisler has been very helpful in helping us track down issues. Most of the issues we've encountered were related to the memory management unit. Basically, this API has not been thoroughly used before, and as we've used features for the first time, we've encountered issues that Geisler has issued patches for to correct in the BSP. Now moving on to debugging capabilities. After you develop a program in a multi-core system, debugging is a little bit more difficult. The traditional debugger tools often do not work in the multi-core environment. Specifically, we encounter a number of cases where Gurman came in and interrupted the process. Gurman is Geisler's debug tool, and that therefore prevents us from using the Wind River dynamic debugger. And when a core interrupts it, it does not necessarily tell you the error if the error occurs on a different core. So it takes a lot of trial and error on occasion to determine where an error is, and from there in order to isolate, reproduce, and fix it. Once we managed to isolate issues, we were able to correct it rather easily. In several cases, switching from our dual core to our quad core system gave a much easier ability to debug. Basically, the quad core system lets us take an extra core and assign a task to it by itself, and therefore help isolate where the issue was actually occurring. There we go. All right, so continuing on, for overall, the BSP for VxWorks has worked in the end. We did have a number of difficulties as we began, primarily focused on the user mode stuff. Geisler has been very helpful in working through our issues, and as I've said, several patches were issued. We've encountered a number of issues throughout our development, things such as exception handlers, assigning tasks to multiple cores, and other miscellaneous issues. Almost all of the issues that we have encountered have been solved. Geisler has been very helpful with that. But there are certain issues we did encounter which, while we are no longer able to reproduce, we're not 100% certain that they've been solved. So our view of the VxWorks SMP is that it is it works. It provides a lot of possibilities for future multi-core architectures, but more testing and usage is needed before we can be confident that it's reached the maturity that's needed. Our testing so far has shown that it mostly works, but more testing is needed. Now, we've also on this IRAD looked into RTEMS. RTEMS supports asymmetric multiprocessing. Asymmetric multiprocessing, So in RTEMS for symmetric multiprocessing, each core requires a separate image. So basically, we started out with our existing RTEMS CFE implementation and created a second image to run on the second core. Doing this, we were able to get them to run correctly with no modifications, each running the same software set. The main changes needed to do that is adjusting the memory map. So the first core runs at the beginning of RAM. The second core has an image that runs at some memory offset from that. The cores can communicate with each other using shared message queues. It's a defined feature in RTEMS that requires a change to the configuration. One of the main differences in the AMP mode is that to actually execute, use a Gurman script, you have to start each core separately. You load each core and set the stack pointer and execution pointer on each core. It's a little bit more time consuming, but it does work very easily. In our experience with RTEMS AMP, everything from the operating system perspective has worked out of the box without difficulties. AMP, however, was not our main focus on this IRAD, so we didn't spend a lot of time on it. We did proof of concept to show that we can communicate between the two different cores. So we would have one complete CFE instance and operating system on each AMP core, and the applications would use what's called a software bus network to communicate between them. This is the same method I may not have mentioned earlier that's used in the user mode version under VxWorks. Excuse me. All right, continuing on. So, main advantages for AMP is that each core is fully isolated in its CPU usage. If an application fails on one core and it does not bring the system to a halt, the other core continues running without any issues. There's less complexity in terms of synchronization and configuration needed compared to SMP. You basically set up your images and you're done. Although obviously compiling the images takes a little bit more effort. The disadvantages in AMP versus SMP is loading process is more complex. An application instance also cannot migrate between cores. As I discussed earlier, under SMP mode, a task can start execution and the OS will dynamically assign them between cores. For AMP, you don't have that option. You start on one core, you're stuck on that core unless you actually stop and relaunch it using some feature that is not part of the operating system. Now, I mentioned difficulties with debugging in SMP mode. The same features also apply to AMP. In AMP, though, it's a little bit simpler in that you don't have tasks dynamically changing between cores. So, makes things a little bit easier. All right. So, continuing on, one of the main advantages in multi-core system in general, taking SMP and AMP considerations aside, is power savings. At least on the Leon processors and most of the other multi-core systems we've heard of, you can actually disable a core or send it into a low power state. On the Leon, there's effectively a low-level sleep operation that, when running, takes the processor into a very low power state until an interrupt of some sort wakes it up and it resumes normal operation. For a single core system, you can do that when the system is completely idle. In a multi-core system, you can implement one idler per core, and when the core is idle, it'll go into a low power state. That low power state, we have found, is equivalent to having the system off and significantly reduces power consumption. The only issue for a low power state is on the multi-core system, AMP mode. That's simple. You just have the extra core completely shut down or enter an idle loop. In VxWorks, you have to manually transfer all tasks off of that core, and then you can bring it to sleep with an idler task. That means you need to be aware of all the tasks in your system, and any task that's assigned to run on a given core that is currently active, you must explicitly deactivate or change its affinity to a different core before you can actually disable that core. The advantage of disabling the cores is you're reducing power and dynamically adjusting the amount of CPU resources you have available. For example, in a cruise phase in the mission, you may have very low CPU resources and only require one core active. Then as you approach your target encounter phase, you can activate additional cores to have the additional CPU resources necessary to do the computing that you need. And I went through this a little bit quick. There's a lot of information here. I hope this presentation has been useful. Any questions?
This question is, you mentioned the previous IRAD to support MMU and computing-only systems. And one of the things your presentation had up there was that each RTP or POSIX process needs a complete instance of CFE. I was just wondering
This was actually a design decision made during the development of that IRAD. You can conceptually design a system in either way, where you could have one CFE instance that's shared between the processes or one per process. For various reasons, it was easier on the IRAD to do the initial development as a complete CFE instance per core, with some additional shared resources in the kernel mode to manage the system.
I can actually answer that question. I was the PI for that. The main driving factor for having a separate image of CFE for each process was basically well, we had looked at making CFE a shared library, but that actually required extensive changes to CFE itself, having to do with the processing of message IDs. Like, there are CFE services, CFE tasks, and they want to, so they would be part of the library. You have to make them part of the library. And so they would have a common message IDs for handling events. And so you wouldn't be able to distinguish between one CFE process and another CFE process. So we actually did go down that path and look at the changes that would be required to make CFE a shared library. And they were extensive. We did make the changes, but we ultimately set them aside because the likelihood of trying to get those changes, those significant changes, merged back into the CFE line of development, that would have to be tabled and looked at a later date. It's doable, but the low-hanging fruit was to make individual CFE images for each process.
So just to follow up, the software bus is part of CFE, and these different processes need to communicate on it. So I assume each process is not running as under its own separate software bus.
It is. And
So then each process is maybe multiple CFE apps in one process then?
Yep.
correct.
So they're really separate domains of,
That's correct.
Okay.
And then they would be linked together. Goddard has developed a software bus network application that you can use to bridge the different CFE systems together, just as you would if they were on separate single board computers.
Go ahead.
So you mentioned application on each core is totally isolated, but on the multi-core processor, different cores share some hardware resources like shared bus, main memory, maybe the level 2 cache. So how do you isolate application on each core?
Well, there's two aspects to that. By isolated, I mean primarily they're isolated in terms of CPU resources. So a core operating on one system does not interfere with the execution time of a core on the other process. The MMU obviously allows the memory isolation when you're in an SMP system, so each task is memory isolated. In the AMP system, each core has all of its CPU and memory resources effectively isolated. The actual hardware access, that's obviously at a lower level. Certain hardware resources, interrupts, access to drivers, those are typically bound to specific cores that have access to those. Did that answer your question?
Yeah, but if you totally isolate different applications, how do they share some data or communicate with each other?
Okay. So in SMP mode, VxWorks provides the resources to share data between them, message queues and semaphores. These are the same standard interprocess techniques that you have in the uniprocessor system. For RTEMs in the AMP mode, when I described how you configure the images, you actually configure a small shared memory region, normally at the beginning of RAM, and in that region, the operating system is able to create shared message queues that can communicate between the message cores, and between the CPU cores. Sure. Go ahead.
I'm not sure if this is possible with your hardware, but did you look into doing frequency scaling as another way to solve power, save power?
Not as part of this year's efforts, but we have done that in the past. You can change the CPU frequency of the hardware to run at a slower speed, but that needs to be done by physically changing a clock on the Leon. In theory, there may be other processors out there that can do that dynamically.
You have looked into pros and cons of AMP and SMP.
Yes.
I wonder whether you have considered also verification efforts for one and the other with respect to meeting timing constraints.
I'm sorry, say that again?
If you considered verification effort needed, for instance, for the model you presented for SMP, to prove that your system can meet timing constraints, timing requirements.
Right. So as part of this effort, we haven't looked into testing and verification of a system. In a high level, though, especially for an AMP system, you could treat each core as a separate processor, so your same standard techniques for verification should work. In an SMP system, particularly when you have tasks that are dynamically changing between cores, that is a more difficult problem to verify, and that's not an issue we have looked into yet.
I was just going to point out that in the RTIMS AMP, the message queues are only used internally by the operating system. That actually, they're used to, you can use regular message queues at the API level, semaphores. You can do things like change spice priority across the nodes and things like that. So your application is using normal services. That was the only thing. And we had SMP, but it was added after you probably started.
Right. I think I had a note in the slide that at the beginning of this IRAD, the state of SMP and RTEMS was not usable for us, but it may be now. Yeah. Ideally, we would like to look into RTEMS SMP, but it's end of the year.
The other thing about the AMP, the caching, nobody from the president mentioned it. Caching effects on these processor configurations is really complicated, and moving tasks around and then predicting the cache impact and the throughput impact is actually really complicated. It's probably still an open problem to solve. And the AMP is often, even though it doesn't sound as good, is often easier to analyze to get your worst case utilizations.
Right.
So, I mean, this is really complicated stuff no matter what you do, and it's complicated on you guys' side, because it's just hard.
Yeah, and for the VxWorks SMP, the notes in the documentation about Affinity, one of the reasons of using Affinity to lock a task to a specific core is if it's executing in large amounts of data or executing on and off, you want it to stay to one core to optimize cache usage. Any other questions?
All right.
Okay, thank you.